Okay, well, totally fine. I think during this time, like many of us who have experienced Zoom the past few months, there's certainly a chat feature. So feel free to chat as everyone is speaking, but we'll go ahead and get started with our speaker tonight. I want to welcome Ed Baidoo. Got the last name correct, I think. So welcome. Ed is currently an assistant professor of decision sciences and management at Tennessee Tech in Cookeville, one of our sister colleges over in Cookeville. So I get over to Cookeville actually pretty often because my parents live in Knoxville and we meet there for lunch pretty frequently. So I'm familiar with the area. Ed has a PhD in analytics and data science from Kennesaw State, which, as we were talking about earlier, is a university that's really kind of up and coming on the data science scene and really kind of pushing their informatics education. So it's really exciting to have you here tonight, Ed, representing them as well. So Ed works primarily in economics and finance with a focus on credit and lending models, which I find super interesting. I'm not in the finance space, but certainly would be excited to hear about some of that work. I also read on his biography that you teach business analytics and advanced business analytics at Tennessee Tech, so that's exciting as well. So without further ado, sorry, that was a really poor joke. Without further ado, welcome Ed, and please would love to hear about mathematics of deep learning.
Yay, excellent. All right, everybody, thank you so much for having me. I appreciate that. Well, let's see how I can share my screen. Oh, well, host disabled participant screen sharing, so I guess I need permission.
All right, let's see if I can do that.
You should be able to click the down arrow next to the share, and then it will bring up 2 or 3 options, and one will be allow multiple users to share.
Got it. Okay, I clicked on that. Can you see it now, Ed?
All right, let's see. Awesome, here we go. We're in business.
Thanks, Charlie.
Right, okay. Can everybody see my screen? Okay, great. I see a lot of heads nodding, so I'm going to take that as a yes. So thank you guys so much for having me. Thank you, Lindsay, and thank you, John, and everybody who helped organize this. My primary area of research, really, like Lindsay said, you do credit risk modeling, especially when it relates to banks. I have interest in actuarial science, economics are one of the things that I do, finance, because that's primarily where some of my background is coming from. So I'm trying to kind of take data science in that realm, so to speak. So that's primarily what I do. So today, what I really wanted us to talk about is the mathematics behind some of deep learning architectures that we have. As we all know, deep learning itself is, well, it's deep, and that's probably a corny joke, but the whole essence of what I wanted to get across is that the breadth is very, very far. There's just way too many things in deep learning. And essentially what I wanted to do is just to talk about some of the math behind it, because it helps really to kind of demystify some of them. And with that said as well, I didn't also want to go too much into some of the stuff that we do there. I didn't know the background of all of us here. So I just wanted to keep it as, friendly as possible. Let's put it that way. All right. So then here, these are the objectives that we will talk about today. We will start by going over graphs and talk about feed-forward neural networks, give some examples of them and how they work. And then, of course, we'll talk about the back-propagation concept. And I wanted to talk about that because it is the key, the essential cog in this whole neural network stuff. And if care is not taken, you get lost in the weeds and you kind of lose the concept behind it. And then I also talk a little bit about recurrent neural networks. I give examples. And then at the end of it, I go over some activation functions that are out there and some loss functions out there. And the reason why that I do that is because it is a current hot area for research that people are still talking about. So it's nice to have an idea of what some of them are currently at the moment. All right, so let's talk about graphs. I have to be honest, the first time that I heard about graphs, this was not what I expected. Especially when you go through first grade, second grade, all that kind of stuff. Nobody talks about graphs in this context. So what are graphs? The picture that you're seeing are, mathematically speaking, that's what we call graphs. So graphs are nothing more than when we have node. So these are the node, and then you have edges. And of course, you have one node, and that's connected to an edge. And there are many different types of graphs and different types of algorithms that you run on them, mathematically speaking, to accomplish something. So for example, a good example that I always give is when you put your GPS and then you say you want to go from where you live to where you work. The question really is, do you want to get there faster, or do you want to take the shortest route? And these are algorithms that we run on graphs to be able to get you, especially if you're going to get there with the shortest distance. It's called the shortest path algorithm. But graphs are essentially really nice way to display relationships. And as you can see, this graph that you see right now has arrows, right? And graphs that have arrows are what we call directed graphs. Why? Because, well, they are directed. So that's why we call them directed graphs. The ones that does not have arrows are what we call undirected graphs. So there's no shortage of imagination there. And of course, if you look at them, you would see that these graphs have what they call weights on them here. So these weights can represent virtually anything. So for example, let's just say that this is city A and you want to go to city B. The weight can be the number of miles that is between the two cities. If you're flying from one state to the other, the weight could be how much it costs to go there. And so this is essentially graphs, and we're going to see where they come in with respect to neural networks. So where have we seen graphs being applied? Well, for example, network analysis. In accounting and especially in finance, we can use graph to detect a network of fraud. So if you want to see if there is a network of people who are trying to game the system per se, especially with insurance, you would see that they form some kind of a fraud, and we have a fraud network. The second one, social networks, is really applicable to virtually everyone. So for example, you have Facebook or LinkedIn. How does LinkedIn recommend a connection to you, right? Or how does Facebook recommend that somebody is your friend, or somebody might be a friend? And those are the stuff that we run graphs on. Especially, it's called link prediction. So in other words, you're trying to predict which two node would have a link in there. In the terms of computer science, we have obviously computer security, where you have networks, and if there's going to be some kind of a network that will be infected with some kind of a virus, how much is it going to take to get there? So graphs in general are essentially very good tools if you know the relationship between two things and you want to understand how one thing affects the other. When we go to operations research, there's something called a transportation problem. And the transportation problem is really intuitive in the sense that we want to minimize the cost of something. So if you are UPS or the post office, what you want to do is that you want to find out the route that would minimize some kind of cost within the network that you have. And that's where graphs come in. It's called a transportation problem. And then this one here in biology is the food web. And of course, the food web is where we put, all animals there, and we know which ones are predators and which ones are not. And it allows us to actually understand the ecosystem. So graphs are essentially, they're very important. Mathematic in nature, very much so, but they are important. So How are they used in data science? Well, in data science, what we use it for is to describe deep learning architectures. And most importantly, we also use it to store data as a data structure, right? So we run algorithms on them, not the same algorithms that we would run on the pure mathematics sense. So for example, in mathematics, when you do graphs, you would run something like the breadth first search algorithm on that. But in deep learning, we're not interested in the shortest path to something. It could be that we may be interested, that's another topic, but in the sense that we're doing it now, what we want to do is that we want to store information within those nodes, and they are easier for us to recognize what is happening there. All right, so now let's talk about the feed-forward neural networks. So feed-forward neural networks are universal approximators. And what is the meaning of that? That means that for neural networks, or feed-forward neural networks, we can use it for regression purposes, or we can use it for classification purposes. I'm not sure if I could go into the details of what regression means or what classification means. So regression simply means that you're trying to model something where the outcome is a numeric number or a number, let's put it that way. There are many different types of where you stand, whether it is going to be an integer or what is going to be a decimal. That's a different types of regression that you could use. But and then we have classification tasks. And classification tasks, as the name suggests, is when you're trying to classify something. And deep learning has done really, really good works, especially in the area of computer vision, where you're trying to classify images. And they've done very, very good work with that. So feed-forward neural networks carry the information in one direction. That's why it's called feed-forward, because you're just feeding the information forward. The only way that we kind of go back per se, and I put that in quotes, is towards the end of it where we're done with pushing the information forward, but we just want to know, hey, where are the mistakes that lie in there, which we'll talk about at some point. So the third thing is that there are no self or feedback loops. So for example, if we look at these graphs here, X1 obviously is this node, X2 is that node, X3 is this node, and X4 is this node. And as you can see, all the edges are just pushing forward, and that's where we're going. However, if let's just say that we stopped here, and this edge right here didn't go forward like this, but it kind of went back to itself. If it went back to this specific node, or if any edges here went back to itself, that is what we would call a feedback loop. Now, we don't have that in feed-forward. We have that in recurrent neural networks, but we don't have that in feed-forward. So in feed-forward, the concept is quite fairly straightforward in the concept that, or at least in the regard that we have the data and we're pushing it forward as we go along. All right, so we can't talk about feed-forward neural networks without talking about what started the whole thing in the first place, and it is something called the perceptron model. So a perceptron model is essentially a model that looks something like this. So in essence, what we have is that we have inputs. So these X0, X1, and up to X3, these are our inputs. And just like how in the concept of the graphs that we also have weights that represent that. So in the sense, we have two nodes that are connected by an edge, and we have also the weights associated with it. So that's where we use the concept of graphs here. Now, each of these nodes have weights that we are going to push forward here, and then it's going to give us an output, right? So in terms of mathematics, how does that look like? Well, the X0 is what we call the bias term. And the bias term is necessary especially when we talk about a linear prediction. In terms of statistics, you need that because of your experimental matrix. You need a column of ones in there to be able to identify your y-intercept. So that's why we need this X0 there. However, what we do for perceptron model is that each of these nodes have a weight that's attached to it. So you can think of it in terms of the brain and how it works. If if this is some kind of a memory, there's a connection between this object and that object, and the weight here would tell you the strength of that connection, right? So what we're doing for this perceptron model is that we apply this weight times the information, the weight times the information, the weight times the information, and then we sum them all up. And then the question is, well, if that sum goes beyond a certain threshold, then the neurons would fire. Then something would we would classify something as 1 or 0. And that is what this equation here is saying. The first one, S, is nothing more than the sum. And by the way, one thing that I wanted to explain is that when it comes to deep learning in itself, one of the things that's a setback is that we don't have a systemic symbols to describe things. In other words, you can find a paper and somebody will just choose their own symbols to describe a couple of things. And that's what feeds into making it kind of difficult to understand what's going behind. So if you see me representing this as, I guess in some sense, I'm also contributing to that headache. But that's what the S stands for. The S stands for the sum. And I felt like it's a nice representation of what's going on. So in any way, we multiply each weight by each input, and then we simply say, well, the sum, if it's greater than some threshold, then we can classify it as a 1, otherwise it's a 0. Now, obviously, when we do that kind of work, we're not going to have our prediction 100% right. So we need to find a way to adjust these weights or the strength of the information so that we get the proper prediction. And this is how we would do that. We do that by updating the weights. So the new weight is nothing more than the old weight times this funny looking n, it's called eta. So we have eta multiplied by delta times the original x amount. So if you look at delta, delta is really nothing more than the prediction error, right? It's nothing more than our prediction minus the old one. And eta is what we call the learning rate. So the learning rate is important in the sense that it helps us to either learn fast or learn slow. And it's also important when we do optimization at some point. Now, the issue with the perceptron model is that it is linear. In other words, if we have data that we have some kind of a nonlinear element in there, the perceptron model doesn't really help us very much. And it's quite easy to see, considering the fact that when you sum them all up, what we get is a linear function, y equals mx plus b. All right, so being that that's not so helpful, let's talk about cases where we can have nonlinear situations. And that is where we come up with what's called the multi-layer perceptron. So the multi-layer perceptron is essentially the same as the perceptron, except that we have multiple layers. We have some kind of layers in there. And this is that's what this thing does here. So we sum them all up. As usual, this is the S for the sum. And then after we sum them all up, we have what's called the activation function. So the activation function is now in control of what's going to happen with our prediction. So in this case, the popular activation function that we use generally in research and also in practice is the sigmoid activation function or the sigmoid function. There are issues with the sigmoid function, definitely. But I think traditionally with introductory level neural network stuff, the sigmoid function is what is introduced. All right, so if we're using that, I felt like I wanted to talk about why, or some of the important aspect of the sigmoid function. So number one, they are nonlinear. And they are nonlinear with respect to the aspect that here the output varies nonlinear with respect to the input. So whatever it is that you give it as an input, we will end up with some kind of a nonlinear output. And the second one is that they are bounded, right? And in this case, they are bounded between 0 and 1, which is why they're ideal if you want to talk about probabilities. And the third one is that it is continuous. And this is really, really, really important. It is continuous. The importance is that it helps for optimization purposes. And when you're doing neural network, or at least in some kind of statistical learning, optimization becomes very, very important. And continuous functions are like the holy grail. All right. So now we can talk about the backpropagation algorithm. And what I want to do is talk about the background and slowly get to how that concept is framed. So the first thing that I want to do is let's talk about the concept of error. So for neural networks, there are about two types of errors that we encounter. The first type, that they are what I call the local and the global. Right? So the local errors are the immediate errors that you would get. So in other words, as you make the prediction, you simply compare the prediction with what's out there. That is your local error. And then there is also the global error. So the global error is more like, well, let's look at the architecture in general, and then let's see at which point does the error permeate through the entire architecture. So to do that, we will need loss functions. So loss functions are functions that are used to actually kind of help us with the accuracy of our prediction. If the architecture that we have is good, is it bad, with respect to the loss functions. So one of the popular ones that are out there is the mean squared error. And the mean squared error is good for regression analysis. There are others that you can use for classification as well, but the mean squared error is good for regression, and that's just an example. All right, so here, let's talk about an intuition for the backpropagation algorithm. So we have a graph, or we have an architecture. And I wrote a couple of stuff here. So let's go through the notations. So H sub I, J, it will be the hidden neuron. So these are what we call the hidden neuron. And they are called hidden because they are not exposed immediately to the original input, right? So these are the input, and these are the hidden neurons. And then of course, this will be my output. And the output just comes out here with my prediction. Now, so this is hidden neuron, and we have two neurons, one here and one two, and that's the second one here. So what we're going to do is that we're going to calculate how the feed-forward neural network works. And then after we've done that, we would see how the backpropagation works with respect to how this is done. So let's just keep in mind, this is just H1 here, and that is just H2. So we're going to do the calculations from the input to H1 here. And all we are doing really, when it comes to neural networks, I think one of the beneficial things is simply just to follow the arrow, right? So in this case, for H1, we have A1 here, and we have A2. So what we're doing is that we're simply just going to sum them up in the first place, right? So every input to H1, we simply multiply by the input, and we sum them up together. So that's exactly what we have here. And here it's simplified from the perspective that x naught or x0 is a biased term. So it's equal to 1. So if it's equal to 1, this is what we get. And then after we're done, there are two calculations that's happening here, because let's not forget the graph structure that we're dealing with here contains data, which is what we use for in neural networks. So after we sum them up, we apply the activation function. So the activation function for the sum looks like this, and that's where we stop for H1. Now, let's do that. Let's do the same thing for H2. So for H2, we sum the weights with the input. We sum the weights with the input, and this is what we get. So at least for now, we know what's here, and we know what's here. And carrying on, we're going to do the calculation from the hidden neurons to the output here. So these are the weights here, and these are the weights here. So we need to get the sum. We multiply this by that, plus this times that, which is exactly what we see here. Now, when we get here again, of course, we need to apply the activation function on that also. So when we apply the activation function on that, this is what it looks like. I'm just comfortable with just changing this to the exponential form here because it looks cleaner and because of what's also about to come later. But clearly, as we have this, we already know that H1 sub 1 is another thing all by itself. We also know that H2 sub 1 is also another thing all by itself. So it's just a matter of just plugging those in here to see what the activation function looks like at that point. So this is what the monster looks like, right? So this is how it looks like for the activation function for the output. This is it. And we already know H1 sub 1 is equal to that. H2 sub 1 is also equal to that. So when we put it all together, this is what the function looks like. Now, the key to really understanding the backpropagation algorithm is to know that at the outset here, the output that we're going to get is a function, right? And that function is a composite function. It's a composite function that is composed of all the activation functions that we have used up until the last one here. That's the key. You need to know that, and if you can, and if you look at it, here we used only one layer and 2 hidden neurons, right? So if one layer and 2 hidden neurons gives us this monster looking thing, you can imagine how many layers and how many neurons would do that. And I believe that this is one of the reasons why it makes neural networks a little bit intimidating to follow, right? Because even if you do just this is just fairly easy to look at. However, the mathematics just looks very, very long, right? But the important thing is that when you're done here at this last stage, and if you look at this function, all of a sudden the function is composed of your weights and your inputs. So if I'm looking at this function, I have my B1 here. B1 is my weight here. And I have my B2 here. B2 is my weight over there. And I have my A naught. A naught is here. So somehow after I move through all of this and I come here, I have a composite function with all the weights in there. And the important part of that is because when we try to do the optimization, we want to be able to find the derivatives with respect to these inputs that will give us the weights that we need to be able to be updated. That is the key. Now, here, this is the error. So the error, of course, we're going to use the mean squared error. Let's just say that we're going to use the mean squared error. So if we use the mean squared error, we know that this is our prediction. This comes all the way here, right? And then we just stop right here, right? This is nothing more than a composite function that we have. It is the same thing as say that you want to find the derivative of parentheses x minus 2 squared, right? Of course, it just looks ugly, but this is what's happening here. Now, after we're done here, it's important to stress this point, the chain rule. The backpropagation algorithm is nothing more than the chain rule that we have. So if we look at the chain rule is used for finding the derivatives of a composite function. And I think, again, that's the key. The key is that you're going to end up with a composite function. And a composite function can be composed of multiple functions. In terms of the neural network, if you have a really, really deep neural network, you can have hundreds of composite functions, right? And that's why it takes long for the neural network to work or to train, because there's a lot of computation that it has to do with respect to the composite function. So here, if we have a differentiable function, two differentiable functions, f of x and g of x, and let's represent let's big f of x be its composition or the composite. That is, if we have this and we have f of g of x, the derivative of this is nothing more than the derivative of the outside function or the parent function times the derivative of the child function here, what's on the inside. So having this, or having known the chain rule, we're able to find the derivative of something like this, right? With respect to this weight, with respect to this weight, with respect to that weight. Now, why do we do that? Well, in optimization and in Cal 1, what happens is that we talk about something called the local minima and the local maxima, and we do all that with respect to the derivatives that we have. So it turns out that when we have a function, and if the function is differentiable and continuous, and we find the derivative of that function and we set it equal to 0, we come up with something called the critical points. So the critical points of the function is where potentially the local minima or the local maxima can occur, right? So that's the first derivative. When we take the second derivative of that said function and the second derivative is negative, we can be fairly certain that we can find the local maxima there. So with respect to the backpropagation algorithm, what we want to do here is that we want to minimize the error, because this is just the error. So we want to take the derivative of this with respect to these weights, right? And if we want to do additional work, we can also take the second derivative of that and see the sign of that second derivative. If that second derivative is positive, then we know that we have some kind of a local minima there, which we can work with. Now, so that pretty much kind of ends with the intuition behind the backpropagation algorithm. The point that I guess I want to drive home is that when you're done with moving the network forward, like for example here, when you're done with coming all the way, you're moving through the network and you come here at the last end, you're going to end up with a function. And that function is a composite function of primarily all of the activation functions. Now, clearly, if you look at this, this is nonlinear, right? And that's why the neural networks are very, very good to search through nonlinear patterns. Because as we go on and on and on, I end up with a composite function that is able to really sift out any nonlinear relationships that I have there. All right, so let's talk about recurrent neural networks. So recurrent neural networks, on the other hand, actually quite easier. In terms of calculation, they are actually quite easier and nicer to work with more than feed-forward. For recurrent neural networks, what we have is that we have XT. So this is sequence data, right? I guess I should start by saying that. It works with sequence data. So sequence data could look like time series data. I think that's the most popular one out there. So if you have time series data, recurrent neural networks are pretty much good for that kind of stuff. Unfortunately, time series data does not really work well with the feed forward that we were talking about, because we have dependencies in there, and the feed forward does not capture the dependencies. But here we have a network, a recurrent neural network that does that. So XT is our input. So this is our input. Now, I use the word sequence here, and the sequence, so for time series, we talk about it with respect to time, maybe lag 1, lag 2, or whatever, what have you. But recurrent neural networks are not necessarily only useful for time series data. It's also useful for language processing and that kind of thing, because in a language is nothing more than a sequence of words that you have to string it together where the sequences make sense. So for example, the boy is going to school is a sequence. Now, we can take each word and permutate each word. The boy is going to school, probably about 6 words together. So 6 factorial, you have a whole bunch of permutations to work with. Now, those sequences are important. The boy is going to school. It wouldn't make any sense for somebody to say going to school, the boy is. Not so much, right? So that's why the sequences are important. That's why the word sequence is there. So in terms of time series, if we have lag 2, or if we have lag 1 will be one sequence, lag 2 will be another sequence, on and on and on and on and on. So we have our sequences here, and then we have what we call the hidden state. The hidden state here works somewhat just like the hidden neurons that we have, and of course we have the output, which comes here to our y hat. So how do we calculate the hidden state? And I say that for recurrent neural networks, they are quite easy to work with, because all you have to do is just follow the direction of the arrow, right? So let's start with HT. We always start with HT because we don't know what came before. So we start with HT, and then gradually we work the information. So HT is here. HT is a function of W. W is the weight here, and the weight is coming from HT minus 1. So here we are. So W times HT minus 1 plus U. Well, here, HT, U is coming from here, right? So U plus XT. So in other words, if I have this HT here, what is acting on HT? So far, I see two nodes acting on HT, this node and that node. And then what I have to do is simply multiply the weight of that node by that, and that's what I have my HT. So in that sense, it's very, very easy to work with. So the function itself is a nonlinear activation function. So there are many activation functions. Like I said, we will go through some of them. So the function is itself a nonlinear activation function. And A is the biased term, which actually we can also train the network to figure out A as well. All right, so the second here, so if we're able to calculate HT, the next one will be to calculate the output as well. So again, what we want to do is to figure out what is acting on the output. So in this case, V, well, this node is acting on the output. So we multiply the weight V times that node plus some bias term, and that is what we have here. And if you realize that for the feed-forward neural network, we were really essentially very, very, very interested in training these weights. But for recurrent neural networks, that's not the case, right? All these are constant. What we really want to know is how we make the prediction here based on the hidden ones. All right. And of course, the prediction here is the prediction here is nothing more than another function of another nonlinear function, I should say. So we're just simply carrying on what is happening through using functions after functions after functions. So it's actually quite easy with recurrent neural networks. Of course, there's also some kind of a back-propagation algorithm here that goes with it. But I think in terms of feed forward, in terms of moving forward, it doesn't give us quite the same, in my opinion at least, it doesn't give me the quite the same amount of headache that a feed forward would give you. Now, so the recurrent neural networks are useful for sequential data. So for example, algorithmic trading. So on the finance side, my folks at finance, they're very much interested in something like this, right? And that's what we want to do, algorithmic trading. And I'm not sure how many people are familiar with algorithmic trading, but it's the whole essence of trading using algorithms, right? Where information that comes in milliseconds are quite important. You want to trade very, very quickly to be able to act on some kind of information. Another thing is, of course, time series data and, of course, natural language processing. Like I had mentioned before, every information or every bit of a sentence is a sequence. And the sequence has to be there if we want understanding with the language that we're using. The second thing is that we have some kind of issues with the architecture that I have just given. That architecture is what we call the plain vanilla recurrent neural network. The issue is something called the vanishing gradient problem. Now, the vanishing gradient problem happens when we do the backpropagation, we do the derivatives, and we propagate the derivatives through the network. It turns out that if we have more network, if we have more nodes and all that kind of stuff, and we push it backward, the weights get very, very small. Very, very, very small. And when it gets small like that, and when it gets small like that, the link or the strength between nodes get very weak, and it doesn't fire as much as we want it to. So that it has that problem there for the plain vanilla one. And however, there's an extension to that as well. The extension is what we call the long short-term models. I didn't talk about it here, but I felt like I just wanted to bring it up there just so that you guys would know that there's the short-term models as well. And then there's what we call the gated recurrent units. These two things, of course, there are majority of some of the stuff that I have said here. You could take the topic by itself and do a whole presentation on that and see how deep you can go. And the same goes for the long-term the long short-term models as well. I know for a fact that we use this definitely for time series. We use this in finance as well. So that's something that's also out there. I had a colleague of mine use this as part of her dissertation. So it was kind of cool and interesting. So now let's talk about activation functions. So activation functions are one area where it is hot in terms of research. So far, I think what I have mentioned is what we call the sigmoid activation function. I think that is, there's a boo-boo right there. It should be a minus. But the sigmoid function is a unique one. It's a unique one that people know about predominantly because of logistic regression and, of course, log of odds and all that kind of good stuff. But the sigmoid function is essential. And the reason why that we use activation function is really to give us that nonlinear element to the neural network so that we'll be able to deal with nonlinear stuff. We have what we call the hyperbolic tangent, and all of these here that I'm presenting, the really important part is that they are continuous functions that you can find the derivative of, right? So if you're able to find the derivative of that, that means, of course, that you can be able to, find the local minima or the local maxima, whatever the case may be. If you have some kind of activation function where you're not able to find that local minima, not to say that it can't be done. It's tough, except that you're going to have to use other optimization algorithms to find non-smooth and edgy kind of a surface, right, to get that. But typically in mathematics, we're very pleased when we have continuous functions that we can integrate and continuous function that we can find the derivatives for. So we have the hyperbolic tangent, we have the softmax here. This is also very popular, the ReLU, rectified linear unit. The leaky ReLU is also very popular as well. And then there's the parametric one as well, and the exponential. And if you look at it really, if you look at the ReLU and the leaky ReLU, the only difference is that there is a coefficient there. And that's quite interesting because when you do the graph, you see that there is some kind of a kink in the graph, which is kind of cool because we need that kink to actually do some other stuff. So it's interesting. And if you look at it, some of these things are nothing more than an extension of what's already out there, right? So it's an active area of research. It's very important, and it is kind of interesting to see what's happening. All right, so here we talk about loss functions. So loss functions are like your guide, right? The guide that tells you, hey, either your model is kind of terrible, and you need some kind of help. So that's what loss functions does. So we have the mean, absolute error, and of course, if all of this, the key point is the word mean. So you're going to find that we're adding something and dividing by something. We're adding something and dividing by something, and that's how these things work. So the mean absolute error is exactly what it is: absolute error, because we're subtracting, and the mean, right? And the mean squared error, again, we square the error and we take the mean of that. The root mean squared error, again, is the same thing. We take the average of something and then we take the square root of that. And then we have the Huber loss. The Huber loss is a little bit different. It may look in some sense like the root mean squared error, but this is how we define the Huber loss. There are others as well, but these, I believe, especially the first three are popular out there to be able to understand what the error of your model is. I think this is pretty much what I have. I hope I haven't bored anyone so far, but I just wanted to share this with you guys. Again, for me, I think the important part about neural networks is to know that once you propagate it through, you end up with a composite function that you need to be able to find the derivatives for.
All right. Well, thank you, Ed.
Sure.
That was amazing. I guess I will get started off with a question, and then we can take questions from the audience. But I was wondering, so I've only built a few neural nets in my time, and I was wondering, do you have any specific strategies for choosing one of the many activation functions out there? Do you have a rule of thumb around what does your data look like and this is the one I should choose, or is it a little more empirical?
Oh boy, if we only knew that, right? All right, so I think that's a great question. So first of all, of course, you start with your you start with definitely your data, right? So if you have what we call a not longitudinal but panel data, right? You have just the normal data that we normally work with. Those are great for neural networks. The essence of which activation functions you use for by and large, it shouldn't really give you too much of too many off things, so to speak, you know. But I do know that for a fact that the logistic regression one, the sigmoid function, it does give you problems, especially when you talk about the vanishing gradient ones. So in that case, it's really a function of how many hidden neurons you have, as opposed to which activation function you would like to use. So what I would probably say is that let's just start with the sigmoid function, give it about 10 layers, increase it to 20, and then see what gives you, how maybe your root mean squared error is and that kind of thing. And then you begin to figure out that, okay, you know what, if this may not be good. My suspicion is that it's based really on the hidden neurons that you have, because one more thing is that when you add more hidden neurons, you're actually making the model more complex by giving it more parameters, because each link that you form you have to introduce some kind of a weight to the link. So each neuron that you give, or each hidden layer that you give, you essentially give the model more parameters to figure out.
Okay, great.
Mhm.
All right. Well, does anyone have any questions for Ed? Feel free to kind of just jump in.
Sure. The activation function gets evaluated many times in big models.
Mhm.
Does it make sense that all other things being equal, if you can not evaluate 3 or 4 exponentials in the process, if you can use a linear function, you're winning just on the basis of amount of CPU or GPU that it's going to take to evaluate those models?
Yeah, I mean, you're right. I think the reason why that deep learning in itself has gathered a lot of attention is because of also, exactly like you said, the computational power that we have. And I don't want to use a word like we're abusing it, but it seems like that's exactly what's happening. But on the other front, it gives us really great prediction with respect to nonlinear nonlinear elements in there. And that's what I think we're chasing for. So for example, you can have like your normal sine function, right? The wavelength function, and say that you have that, and you sprinkle a little bit of error, call it, normally distributed or whatever it is, and you sprinkle it in there. Neural networks can give you that approximation to really good result. But of course, we also sacrifice in that, that mathematics behind it. So, and that's why, honestly, that's why everybody keeps saying it's a black box, right? And well, they shouldn't call it black box, because at the end of it, you just have a composite function. That's all it is. You have a composite function at the end of it. But with the example that we did, that was just two hidden neurons, right? And look at what we got. So you can imagine, what's out there, right? So yes, you're right. It's a matter of saying, well, I'm chasing after some kind of nonlinear element, see what I get, right? Of course, you may not want to go that route. You can even, you can pick something like, a squared regression and see what you get, right? Where you're not doing the normal regression, but you're simply doing polynomial regression, and then see if there is some kind of a nonlinear element in there and see what you end up with. And of course, that's on the basic front, but that's it's just one of those devils that we have to work with. So I see somebody's asking Henry saying, why are GPUs advantageous for neural networks and deep learning? Is that even true? Yes, Henry, it is true. So let's go back a little bit about computers. So when you have your computers, what you have is your CPU, right? And unfortunately, your CPU cannot compute on the same level, at least fast. We're talking about fast. So I'm not even talking about memory space and all that kind of stuff. So in terms of just faster computation, you need that graphical processing unit to be able to do that fast enough for you to get your result. Now, the issue, or at least why that's important, is this. When I was doing my PhD, I had a whole bunch of stuff that I had to run. Now, I would run something, tweak a little bit of, some kind of a weight or something, and I would have to wait 20 minutes for the result. It was a killer. I hated it. I wanted to just punch the computer, right? And what's worse, sometimes I would run my algorithms, and this is an optimization algorithm. I would leave it in my office, or I'll leave it in school, and I have to come back the next day to figure out what's going on with it. It's not fun if you want to finish your PhD, right? So that's why the GPUs are important. You want to have that faster processing time, faster processing speed. Unfortunately, they're very expensive too. So, yeah.
All right. Any other questions from the crowd? We have one that came in through chat.
Yes. So, Anirban, I hope I am not butchering your name. I'm sorry if I am. Chances are I am. I apologize. But so the question is mini batch and batch. Now, so essentially, mini batch and batch comes in when you're training your data. Mini batch simply means that how you update the weights, right? It's in small chunks. So when you run everything, you either say, well, so let me step back. Typically, when you want to update the way, you go observation by observation, and then, okay, this is it. I have to change that. Problem is that as you change one observation, it has some precaution on the next one or the previous one, right? So then that becomes an issue. So then they came up with the batch and the mini batch. That's like saying, okay, you know what? I'm just going to run the epoch on a small batch of my data, and then maybe I'll take the average error, something like that, and then kind of update on that batch alone rather than going through a whole bunch of it. So essentially, when they talk about batch and mini batch, sometimes like when I'm on campus, I tell my student math is a lot about English, right? So you can think about a batch of something, a batch of paper, a batch of whatever it is. So that batch is what they're working on at the moment. And then whatever result that we get, we can take the average of that, and then we work on maybe the next batch and the next batch and the next batch. So that's pretty much that. And in terms of accuracy, it's actually proven that it helps a lot to do it like that rather than doing every single observation one by one. So that's important. And of course, it also helps with processing time.
Okay, great. Any other questions? Feel free to speak up or post a question in chat.
I've got a one. I've heard various things anecdotally from acquaintances using neural networks more, and one was when training image classifiers, and you don't have enough training data, just augmenting things a little bit with some random noise and building up back. Is that something that's generally applicable to different kinds of data? Could you do that with a regression problem? You've got a few hundred things, add a little bit of random noise to each feature.
That's a bad thing. Well, so that's a great question, Matthew. So for image classification, yes, right? And that's because, for example, you could take a picture, any picture, and you can sprinkle some kind of random noise on it, and we can fairly make out what that picture is, right? But when you have real data, so for example, when you have, fraud data, you typically don't add noise to it. What you typically do is that you do the opposite, right? You create more of it in the case where you have an imbalanced data set, right? So in that case, when you have an extreme, that's called rare events modeling. And you see that a lot in insurance and fraud and all that kind of stuff, because it doesn't really happen much, right? So if you're working for an insurance industry, you want to be able to predict when the next tornado is going to happen. But unfortunately, fortunately, it's not like tornadoes happen every day, right? So it's very rare. So in that case, you create more of them rather than putting noise in that specific data. Image classification, on the other hand, yes. And it turns out that, when you put noise on image, it's not in the same sense of how we know it. It's nothing more than putting some kind of pixels, creating some pixels on it, and that's pretty much it. So I wouldn't say there's a lot of harm in that perspective, but when you have real data, you don't want to introduce noise to it. Unless, of course, the only way that I've seen that is you introduce noise to something to see if you've come up with a new algorithm, and you're saying that the algorithm is some kind of a powerful tool, is really, really good. If you're able to kind of distinguish between, between the real data with some noise, that's good, right? So,
cool. Thank you.
Let's see. This is Brandon. When training a text classifier, is there a greater advantage in deepening the network or using more complex set of activation loss functions, particularly when working with a small set of data? So that's the issue, right? The small set of data. In essence, when you have text classifier, I'm not sure if you would be able to, I think that you should be able to have like a fairly large amount of data, especially if you're able to get like a corpus or something like that. Usually corpuses are big, so you should be able to get that. But I think your question really is it good if you're able to mix and match different how do you call it, activation functions? And in the research that we have right now at the moment, we're kind of stale on it. People come and say, yeah, it's good to kind of mix and match. And people say, no, it's not good to kind of mix and match. However, and that's on the research side, but in terms of application, what I find out in the industry, if it works, it works. Right? Industry, we don't really, it's not like we want to come up with some kind of mathematical justification for what's really happening and, all that kind of stuff. But in the industry, if it works, it works. Oh yeah, Viraf also said, yeah, you may want to consider transfer learning, which is also true as well, depending on how small the data is. Yes. Thanks, Viraf.
I was going to mention, I don't really have a lot of experience with like image data, but in healthcare for rare events, I've seen bootstrapping applied often. I think that's maybe what you were alluding to earlier, is that you do sort of multiple sampling of your data over and over again to really get to the true value or the true mean. If you're just doing descriptive statistics, same for modeling as well. But again, I don't know if that applies for image data.
Yeah. You definitely, bootstrapping is like on the statistics side, it's a go-to. On the machine learning side, you could also use KNN, where you can literally synthesize, you can create a synthetic data, and I find that to be really, really awesome. So I think, yeah, that research also is really highly coming up. So that's really, really good. But image, on the other hand, all you have to think about is some kind of a picture from the 80s or something. You see how blurry it is, and
All right, wonderful. Any other questions? We have another one come in via chat.
Oh.
I have two questions about the architectural. So can you get to the slide, right? I think it's 16, right?
You said 16?
Yeah.
There we go.
So, because I'm into development, so I'm really interested in the graph. So, I just wondering, where's the, when you are on the top of the graph, where's the initial hidden state come from?
Okay, good. That's an excellent question. So the initial hidden state is something that we would random. It's like just like how if you think about how you do conventional neural network, you just randomize the weights, right? And then gradually you change it as you go along. So in this case, that's exactly what it is. We don't know the initial hidden state, so we just randomize it, and then we move on and change it, and then back propagate through, and that's it.
So is there any like general rule to initiate the first hidden state?
Oh, good question. So that's also another research area, right? So traditionally, what people do is that I think when I first started learning, like they would just told us, oh, just put zero in there, just make everything zero, right? Then the problem with making everything zero is that if you think about the weights as connection between two things, that means that there's no connection. How would you fire anything if there is no connection, right? And that's where we move from the zero to say, okay, you know what? Let's just randomize the thing, right? And then let's see how that works. What you want to do is just randomize it a little bit, very, very small. I have seen cases where there are how do you call it, rules on how do you randomize certain things. I forgot. I think for some people they just do it like there's a formula for that kind of thing. The square root of 6/3 or something. I don't know, but it's there. It's there. There are research going on there too. So yeah, that's a good question. A lot of people ask that question, and that's a legitimate question because if I can set it up the right way, I don't have to spend all that time train the model and then come back to it and take forever to do, right? So that's a very, very good question. How, where's the right place to start?
Sorry, one more question. So I see in each time step we get a new output, right? So in this graph we get 3 outputs. So we use all 3 outputs to calculate the loss function, or we just use the last output?
Good question. So essentially what's happening is that this is a dependence data, right? And this is where the recurrence comes in. The recurrence comes in from the perspective that we have to go back. So if you look at this HT minus 1, HT plus 1, so there's some kind of a recursive that goes on and on and on and on. And if we look at this function too, it tells us kind of like the same thing, right? This starts with HT, and then we rely on HT minus 1, and then the next one. So the current one becomes feed or becomes fodder for the next one, on and on and on and on and on. And that's where we get that sequential element from.
Thanks.
Yeah, it's interesting. I like RNNs much better. It's easier. The feed forward one, like I said, you do a little bit and you see the math and it's like, it really is, it's in your face. But the RNNs, I find that it's quite simple. Let's see.
All right. Yeah, we're at an hour. I think we'll do one more question on chat about hidden layer sample size.
Okay. Let's see. It says, are there rules of thumb that can tell you how large your training data set needs to be as a function of the number of hidden layers? That's a good question. For example, if you have 2 hidden layers of 20 nodes each versus, okay. So that's a very, very good question. I think generally I'm not sure if there's a rule of thumb, but generally what you want to do is that you want to make your network longer as possible, not wider. If you make it wider and you put in too many hidden layers, that's where you're getting, that's where you make the model complex, because now you have to account for each link, right? Each edge, and each edge gives you a weight, and each weight gives you some kind of a parameter in your model. So you want to make it longer. In that sense, you have many, many neurons, except that you don't have a lot of hidden neurons in there. Of course, there are many ways of dealing with that kind of thing, right? You can have a dropout where, randomly you could just stop a neuron from firing and it's just 0. And of course, if you stop it from firing, that means that every single neuron after that does not really fire, right? So those things are there. You can have the dropout. You can you can also plot as you train. You can do some kind of a plot and you can see at which point the data is sufficient enough per something like your root mean squared error or whatever the case may be, and you could just stop. That's called early stopping. So you just stop it early rather than going on and on and on and on.
Okay, wonderful. Well, in the interest of time, we've definitely had Ed for an hour. So Ed, please everyone join me in virtually thanking Ed for his presentation this evening.
Hey, thank you.
Thank you.
Thank you, Henry.
Well, it was great to see everyone and wonderful to meet you, Ed. I hope to see all of you at the Analytics Summit coming up in a month. And thank you again, Ed. And I hope everyone has a wonderful evening.
Mm-hmm. All right. All right.
Thank you.
Let's see. Yes. Yes, Megan, please. Yes. So just send me a LinkedIn and we shall connect.
All right. Thanks, everyone. Thanks, Ed.
Okay. Bye-bye.